Welcome back. In this video we're going to continue our chat about cyclic subgroups, and we're going to spend this video on one theorem and its corollaries which help us to answer the really important question about when it is that two cyclic subgroups are actually the same thing. One of our overriding aims in this course is to understand how groups and subgroups of groups actually fit together, and we want to sort of be able to understand exactly what the subgroup structure of different groups is. So an important part of this is being able to answer the question of whether it is that two subgroups are actually the same subgroup. Okay, if you take two cyclic subgroups with different generators, how do you know whether or not they generate the same thing, and is there a way of telling this? The answer is yes, there is, and we're going to dive in and look at some theory that helps us with this question. Okay, so here is our theorem. It looks innocuous at first, but it actually tells us a lot. So let's just read it out. Let A be an element of order n in a group, and let k be a positive integer. Then we have a statement about whether or not, or it's telling us that a to the k, the cyclic subgroup generated by a to the k, is the same one as the cyclic subgroup generated by a to the greatest common divisor of n and k. Now we've kind of observed this before, just informally, when we've looked at, say, the U groups, and we've looked at the cyclic subgroups generated by each element. And sometimes we saw we got the same subgroup with different generators. And then we can make a corresponding statement about the order of the element a to the k, and it turns out to be n over the GCD of n and k. Alright, so before we can make use of this though, of course we've got to prove the thing. So let's get cracking on that and see how we get on. Right, so what do we got? We've got A as an element of a group with order n, and k is a positive integer, etc, etc. Okay, now we need to make use of the GCD, so let's just define that. So I'm just doing a little bit of setup here. We need to define a couple of things. So let D be the GCD of n and k. And it's going to help, because D is a divisor of both n and k, let's express k in terms of D, and let k equal D times whatever you have to multiply D by to get to k for some integer r. Okay, so that's just a little bit of setting up some symbols to match the information we've been given. So we don't need to write down GCD all the time. We'll just call that thing D. Okay, now we'll focus our attention on the first part of the proof first, this one here. We are being asked to show that two subgroups are the same thing, which is, or you could think of this as we're trying to show that two sets are the same set. So the way we tend to do this is if we want to show sets A equal B, then if we can show that A is a subset of B and that B is a subset, okay, it's supposed to look like this, but I'm not very good at drawing it. B is a subset of A. If we can show that they're both subsets of each other, then that's the kind of standard way of showing that two sets are equal mathematically. So that's going to be the approach we'll take in our proof here. We're being asked to show that the set a to the k, or the cyclic subgroup generated by a to the k, has the same elements as the cyclic subgroup generated by a to the d. Okay, so let's start by looking at whether or not a to the k is contained within a to the d. So how's this going to work? Well, a to the k, let's just write it out and then you'll see how it works after I finish writing this line out. A to the k is equal to a to the dr. So that's what I defined k to be. It's whatever, it's r times its GCD with n, which equals a to the d all to the power of r. And that, of course, is a member of the cyclic subgroup generated by a to the d, because it's a power of a to the d. Hence, the cyclic subgroup generated by a to the k is contained within the cyclic subgroup generated by a to the d. That's because if I take any power of a to the k, it's just going to be that power of a to the d to the r, and so that'll be what we get. Okay, so that's one way of our inclusion. Now we've sort of got our head around the structure here to show that a to the d is a subset of a to the k, or at least the corresponding statement to that one there. We're going to try and do a similar thing. we're going to want to show that a to the d is contained in a to the k now. That means that d equals k times something. Okay, so let's see how that works. Now, I'm going to make use of the GCD property, because when we've got GCDs, we've got to keep in the back of our heads that we've got this linear combination property of GCD. And that often turns out to be really useful. So I'm going to let D equal NS plus TK for some integers S and T by the linear combination property. Okay, now why would I want to do that? Well, essentially I want to express D as a multiple of K in some sense. So you can see that if I do this one here, then D is a multiple of K plus a multiple of N. And I know that A to the N tends to become E because N is the order of the element A. So that's going to be a worthwhile thing to do, because when we actually plug this in, A to the D equals A to the NS plus TK equals A to the N to the S, A to the K to the T, you can see where this is going hopefully, is just equal to A to the K to the T, because A to the N is just our identity, and that there is a member of the cyclic subgroup generated by A to the K. Okay, so it's the same kind of statement as we had here. A to the K is a member of A to the D. We've done the same thing for A to the D as a member of A to the cyclic subgroup generated by A to the K. Okay, so this means that we have the corresponding subset relationship. A to the D, the cyclic subgroup generated by it, is contained within the cyclic subgroup generated by A to the K. Now if I put those two things together, just get rid of some of this highlighting so we don't get confused. If I put those two things together, what I'm going to get is that, so I'm going to combine this one and this one, then overall I get, and thus the two sets are equals A to the D. And that is the first part of my theorem there. Right, now we need to attack the second part. So we've done the first bit. Now the order of A to the K, as we discussed previously, is just the order of the cyclic subgroup generated by it. And we now know that that's the same subgroup as A to the D, a cyclic subgroup generated by A to the D. So the order of A to the K is equal to the order of A to the D. Now we just need to figure out how big that number actually is. We're hoping to find that it's N over D is what we should end up getting. Okay, so what can we do? Well, D is a divisor of N. It's the largest common divisor of N and K. So what does that mean? It means that N over D is defined. So I can take A to the D to the power of N over D as an integer, and A to the D to the N over D is a thing that makes sense as A to the N, which equals E. What does this mean about the order? Well, it means A to the D to the power of this number is the identity. And that means that that number there is either the order of A to the D or it's a multiple of it. So hence, the order of A to the D is less than or equal to N over D. All right. So now we're just going to establish that we can't have the order being any lower than N over D. So for an integer, a positive integer I, which is smaller than n over d, we're going to show that I can't be the order of a to the d. We also get that id is less than n. D is positive, and hence a to the d to the I equals a to the id, which is not equal to the identity, as the order of a is in fact n. id is less than n. Okay, so you can see what's happened here. Essentially, I established first that the order of a to the d, or a to the d to the power of n over d, gave me the identity. Therefore, n over d is either the order of it or it's a multiple of it. So it's either that number there is either the order or it's bigger than the order. And so I can conclude that my order is no larger than that, because I know I get the identity if I multiply by it, if I set that power. And then I said, okay, well, I'll take a positive integer I, which is smaller than it, and let's see if that can be the order or not. That is equivalent to id being less than n. So I take a to the d to the power of I, and I end up being unable to get the identity, so I cannot be the order. And so I can conclude that the order must therefore be what we want. Hence, the order of a to the d is equal to the order of a to the k, which equals n over d, which is the GCD of n and k. Okay, so let's see how that's the end of the proof. We have shown those two things are both true. Let's just have a little bit of a play on an example and see how it works in practice. So this simplifies discussion of cyclic groups. Makes our life a bit easier. E.g., if our element n has order 30, notice I don't actually care what the group itself is that we're in. I just have an element A that's of order 30 inside some group. Then I know that the order, for example, of a to the 26 is equal to the order of the GCD of 30 with 26, which is 2. Likewise, if I want to know the order or the cyclic subgroup generated by a to the 23, I take the GCD of 23 with 30, which happens to just be 1. So that means that 23 is a generator of my cyclic subgroup. Each step to find out, I just take the GCD with 30. In this case, it's 2 again. And I can make corresponding statements about the orders as well. So I could say that the order of a to the 23 equals 30. The order of a to the 22 equals 30 over 2 equals 15, etc. So you can see that I can actually create quite a few correspondences between different cyclic subgroups now. I can say that quite clearly these two things both have the same GCD with 30, so they generate the same group. So what we're going to do next is we're going to state a number of corollaries to this theorem, which essentially are special cases of the general theorem, which help us to make these kind of statements a bit more concrete. Right, the first of these corollaries is that if our group is actually a cyclic group itself, then n is the order of the group, and the statement says that the order of any particular element of the group divides the order of the group itself. Okay, so a to the k is an element of the cyclic group. The group itself has order n, and so we can see that the order of any element given by this expression here is a divisor of n, which is helpful. Okay, and our second one is a statement saying that two cyclic subgroups are equal if and only if they have the same GCD with n. And you can make a corresponding statement about the orders of these things. Alright, so let's just quickly sketch out how that one works. It pretty much is what we just did with our example before. So let's just say if GCD of ni equals GCD of nj, then a to the I is equal to a to the d by the theorem. So that equals d, sorry. Then a to the I is equal to a to the d cyclic subgroup, which is equal to a to the j by our theorem. And similarly, the order of these things is the order of a to the j, which is going to be n over d. And similarly, going the other way for the if and only if a to the I equals the cyclic subgroup generated by a to the j, then clearly the orders of the elements are the same. Which is going to be turning it into the GCD version of it by the theorem, which equals n over the GCD of nj, and therefore those two denominators must be the same, and so the GCDs are the same thing. Okay, so that's useful. So we have in mind that the two cyclic subgroups are the same thing if they share the same greatest common divisor with n. All right, this next one is a special case of what we just did, and that's it's important enough to just state it in its own right. Essentially, we're just taking I equals 1, because that turns it into a statement about when is an element a generator of a cyclic subgroup. So as we've got a cyclic group of order n, so we've got an element of order n inside whatever group. This forms a cyclic subgroup of order n, and we're saying that the generators, we have two generators if and only if they share a GCD with n of 1. So to generate a group of order n, you must have GCD of 1 with n. Okay, and then there's a corresponding statement about the orders. Okay, so that's a very important one because it says when are two elements both generators of a cycle, or what is the condition for a cyclic subgroup, for a to the j to be a generator of our cyclic group. And for reasons that will become apparent a little later, it's also worth stating this for Zn. It's exactly the same as corollary 3, but now we're just treating our I guess the A to be 1 and the order to be n, so we've got Zn as our group generated by 1, and we're saying that generators of Zn are only those numbers who are relatively prime to n. Okay, and this is actually kind of the most useful version of this corollary because it turns out that all cyclic groups are actually equivalent in some way to Zn. So Zn is the only one we really need to think about. Now we'll justify exactly why we say this later on, but for the time being we'll just actually make this connection with Zn here. So what this means is that if we know a generator, we can find all the others. And that works for any of these cyclic groups. We can find all the others. Alright, so e.g. in U of 50, the order of U of 50, the group, is 20. You can check that yourself. You can write down all the numbers relatively prime to 50 and build up U of 50. And it turns out that U of 50 is cyclic. Again, there's no easy way to know that it's going to be cyclic in advance. Remember, some of the U groups are, some of them aren't. But let's say we've been told that 3 is a generator of U of 50. Again, you could check this on a computer quite easily by just testing it, but it is true. U of 50 is a cyclic U group, and it's of order 20, and 3 is a generator. Now we can use corollary 3. We can say that this is equal to 3 to the j. Okay, so it's the same cyclic subgroup as some other generator, if and only if GCD, the order, which is 20, and j equals 1. So that means that j is a member of 1, 3, 7, 9, 11. These are all the numbers relatively prime to 20, not 50, and 19. So our generators are now I'll just leave them as powers of 3 because actually computing them is a bit hassly, but you guys can go and do that if you want. Just take the power of 3 mod 50, 3 to the 9, 3 to the 11, 3 to the 17, and 3 to the 19. Okay, so those 8 elements are all generators. I feel like I've missed one. 3, 1, 3, 7, 9, 11, 13. 3 to the 13. These are all generators of U of 50, and U of 50 is a cyclic group. Alright, so we'll make use of this quite often when we're trying to understand cyclic groups and finding generators of them, but we'll sort of stash these theorems and corollaries to one side and keep them as handy reference for later on. So that's enough for this video. We'll catch you in the next one. Have a good rest of your day or night.